Welcome everyone to another problem solving session. In this video we are going to talk about three problems regarding the concept of center of mass. And the first problem here talks about a disk which is uniform in terms of mass distribution and which is circular, right? But the catch is another circular portion has been cut out of it. So, for example, in the green shade, it's massive, that means it has mass, and the whole circular disk has a radius of 2r, where r is some given number. And it is centered at the origin of the coordinate system. Then, centered at negative r, 0, we have another disk which is empty. That means its mass has been cut out. So therefore, we have this weird shape where this is all massive, but this white part isn't. Alright? And we're going to find out the center of mass of this shape. So what do we know? We can consider this weird figure as a combination of two disks, one with positive mass distribution and the other with negative mass distribution. So before we do the calculation, you do understand that the whole thing is symmetric with respect to the x-axis. So the center of mass is still going to lie on the x-axis, but just on the massive side. That means somewhere here. And this is what we're going to consider to be our new center of mass, so center of mass, and its coordinate is going to be some value xcm, and the y component is going to be 0 because the whole thing is symmetric with respect to the x-axis, as we have just spoke of it. So then what we're going to do is consider that this bigger mass of radius twice r, so let's just call the density, the areal density, to be sigma, and the area of the bigger disk is simply pi times twice r squared. Now that's the mass of the bigger disk as a whole, where this pocket has not been cut out. So the whole thing had mass initially the whole thing had mass sigma pi and then 4r squared. And the piece whose mass has been cut out, let us call the area density of this disk to be negative sigma, and if you multiply the area with the density, you get minus pi sigma r squared. Okay, so the big one will be called m1 and the smaller one will be called m2. Now, in order to find out the center of mass of the whole system, we need to find the position of these individual masses, right? One for the missing mass, one for the total mass where the circular disk weren't cut out from the bigger circular disk. So the way we can do it is this: the center of mass, so I'm going to put the position vector center of mass, is by definition is given by this formula m1 plus m2 times the sum over individual masses times the position plus m2 and then r2. Now what is r1 and r2? Well, r1 is the center of mass of the whole object and r2 is the center of mass of the missing object, right? And yes, we can use the center of mass of an object as the position for that object, because that's what center of mass was supposed to do. So if we want to find out R1, it's simple. It is the origin. So the whole object, because of the symmetry, there is no other option. It has to be the origin. So x1 would be 0. So I should actually write 0 and then x hat plus 0 times y hat. What about R2? Well, we also have found that out. I have written it here. It's going to be negative r x hat plus 0 y hat. So if we plug that in here, what do we see? Our center of mass is given by, well, 1 divided by m1, which is 4 pi sigma r squared, well, minus pi sigma r squared. And inside we have, what do we have? We have 0 vector. Here it is 0 vector times m1, so that's again a 0 vector, plus m2, which is minus pi sigma r squared times minus rx hat plus 0 y hat, which we can omit for now. So if we try to simplify that, this is where we end up in. So we have 1 over 3 pi sigma r squared times, so negative signs make it positive, and we have pi sigma r squared times r x hat. Is that right? I think it is right. So r square cancels r square, sigma cancels sigma, pi cancels pi, so we end up with r divided by 3 x hat. So that is in the positive direction along the x hat, so it's r divided by 3. So if this is twice r from the center, from the origin to the end of the x-axis, to the perimeter on the x-axis, then this is twice r, right? This is twice r. So I do not have a scale, but we can definitely try to figure it out. So this is just simply r, and it's r divided by 3. So we have 1, 2, and this is 3. So this is where the new center of mass lies in. Okay, so that completes the first problem. Okay, so the next one is problem number 2. We see that this problem is given in the form of a picture. We can see 3 masses, MO, MA, and MB. MO is situated at the point O, which is also considered to be the origin of a given predetermined coordinate system. And MA is located at point A, and MB is located at point B. All of their positions are given in terms of the coordinate system, and their masses are also given, and their velocities are also given. So it's a straightforward problem. All we'll have to do in order to find out the position of the center of mass and the velocity of the center of mass is to use our known formulas and to simply find the answer. So right at the beginning, let's go for the center of mass of this system. So center of mass, RCM, is known to be 1 over the total mass. So that means MO plus MA plus MB, right? And then multiplied by MO times the position vector of the origin, which is actually the 0 vector, plus plus MA times RA plus MB times RB. Alright? Now just plug in the numbers. So if you add all the masses, you get 1 plus 2 plus 1.5. That's 4.5 kilogram, okay, times, well, m naught, which is actually 1 kilogram of mass. I should just simply write 1 kilogram instead of m naught, so 1 kg, but it is multiplied with the position vector of the origin, which is the 0 vector. Then we have mass of mass Ma, which is 2 kilogram, times the position vector of the point A, or the mass A, which is 1 meter x hat plus 6 meter y hat. And then we have the mass 1.5 kilogram, which is mb, times the position vector of the point B, which is given by 6 meter x hat plus 1 meter y hat. So the first term yields 0. The second term, so let's just collect the x component. So we have 2 kilogram and then 1, so that's 2, and 1.5 times 6 meter. So that would be just simply 9 kilogram meter. So 2 plus 9, that's 11, right? Kilogram meter, x hat. And what about the other? So we have 2 and 6, so that's 12. And then we have 1.5 plus 1 times 1, so that's 1.5, so 13.5 kilogram meter y hat, and all divided by 4.5 kilogram. So let me run that by a calculator, and the calculator tells me that this is supposed to be the answer. Alright, so let me box it up. This is the position of the center of mass. Okay, now the velocity of the center of mass, it's the similar method. So velocity of the center of mass is the total mass, and then just simply sum of the products of the masses and the individual velocities. So I should write V here. Yeah, V. And what does that entail into? So we have 1 over 4.5 kilogram, and then we have, so the M0, which is just simply 1 kilogram, times minus 2 meter per second x hat. So I should rather write the result altogether, right? So let me erase that. So 1 times minus 2, that's minus 2 kg meter per second x hat, and then again minus 2 kg meter per second y hat, and then I have to add it to MAVA. So MA was, how much was that? That was 2, right? So 2 times 2 is 4 kg meter per second y hat, and VB would be multiplied to MB. So we have 2 times 1.5, so that's 3 with a plus sign, 3 kg meter per second y hat. So let's just simplify these numbers. So again, 1 over 4.5 kg, and then times 4, sorry, I think this term here was supposed to be just the x hat, right? Yeah, it's a little mistake. This is going to be x hat. So negative 2 plus 3, so 3, and x hat, And then what? And then we have negative 2 plus 4, so plus 2 y hat kilogram meter per second. Kilogram is cancelled by kilogram, and so we have this vector as a result, as indicated by our calculator. So that would be the velocity of the center of mass. Notice, before we move on, the fact that since the velocities, the fact that these results, so for example, this velocity is not a function of time, or perhaps is given at a fixed time. So we cannot calculate the force on the system. But if they were given as a function of time, we could simply take the derivative with respect to time to get the acceleration, and that would be the effect of the net force on this system of 3 particles. Alright, so let's move on to the last one. So in the third and the final problem of this video, we're going to find out the center of mass of a uniform planar object, which is given in the figure. Notice the coordinate with respect to which we are supposed to find out the center of mass is arranged in such a way so that 4 different pieces of this object falls in 4 different categories, or 4 different quadrants. Excuse me. So we're supposed to find out the center of mass of this uniform object. So uniform, which means sigma, the area density or the surface density, is constant throughout the object. So that simplifies the problem by a large margin. But what we really need to do is to employ the technique that each of these objects shall be substituted or be represented by the center of mass, their respective center of masses, that is to say. So therefore, we have these 4 objects. We replace them by their center of masses and corresponding masses, and then we'll find out the center of masses of those 4 objects. So I think you'll get it better as we get along. So first of all, let us choose the object in the first quadrant. So this is for L long. So L is supposed to be a unit of length, and it's L unit wide. So therefore we know the center of mass of this piece is going to be along the 2 meter mark, right, from the y-axis. So that's 2L. I said 2 meter, that's 2L mark, excuse me. And this is supposed to be, very intuitively, is going to be half L distance away. And so this distance here, however, right, is 3L minus this quantity here, which is just L, excuse me. So that is going to be twice L. So twice L plus half. So the center of mass of object number 1 is going to be at along the x-axis twice L x hat plus 2 plus half. So that's going to be 5 divided by 2 L y hat. So that's like the first one. The second one is in here, so it's going to be negative L along the x-axis and 1.5 or 3 by 2 L along the y-axis. So R2 is going to be minus Lx hat plus 3 by 2 L y hat. What about R3? So this is going to be 2 L distance away and then L distance away along the x-axis, or negative L away. So negative L, right? I hope that's correct. So negative L x hat and negative 2 twice L y hat. what about R4? So this is going to be, well, so this distance is twice L on the negative y-axis, and then further down the line we'll have to go half of twice L, which is just L. And since this length here along the x-axis is twice L, the center of mass of this object is supposed to be just L distance away. So L in the positive x-axis plus minus thrice L along the negative y-axis. So we have the center of mass of all of these different pieces just from the figure. Now we'll have to find out the corresponding masses, right? So this is what we're going to do, okay? So since it's a planar object, we have the total mass, capital M, equal to sigma times the total area. And masses of these individual ones, so let me denote that by Mi, is supposed to be sigma times Ai. So from the formula, from the definition, which tells us that center of mass is 1 over the total mass times the sum of Mi Ri. This is going to be 1 over sigma times total area, and here we have sigma Ai Ri. Now sigma is a constant, so it comes out and cancels this one, so this sigma cancels that one. So therefore we simply arrive at this expression, which is our center of mass is 1 over the total area times A1 R1 all the way to A4 R4. Okay, so now let's use this formula. So A1 is given by 4L times L, which is 4L squared. A2 is given by 2 times 3, so that's 6L squared. A3, that is 4L times twice L, so that's going to be 8L squared. And A4 is going to be twice L times twice L, so 4L squared. Now that we have that and we have the corresponding positions, we just simply apply our formula. So if you need to find out the total area, so that's 4 plus 4, that's 8, 16, that's 20. And A4 is going to be twice L times twice L, so that's 4L squared. And therefore the total area is going to be the sum of all of those. So 4, 4, that's 8, 8 with 8, 22, 16, and then plus 6 is 22. So 22 squared. Is that correct? 8 and 8, that's 16. And 6 more is 22. Yeah, this seems to be correct. All right. So then we have 22L squared, and therefore we have the center of mass is going to be 1 over 22L squared times, well, I have to go back and copy all the positions that we have here. So the first one is R1, the second is R2. You get the flavor. So we just multiply them with the corresponding mass. So the first one would be just 4L squared times whatever this is, plus 6L squared times R2, plus 8L squared times R3, plus I think it's 4L squared times R4. Okay, so can we just simplify it? I think we can. So that will give us the center of mass. So we have the coefficient of x hat. Alright, so you do readily understand that all the L squareds are going away. So no point of just carrying them. But the L's will be there. So these single L's, they will be staying. So we have 1 over 22. And then what? Then we have, well, take the L out. So L over 22. And we have 4 times 2. Right, so that's 8 minus 6, so that's 2 minus 8, so that's minus 6, and plus 4, so that's minus 2. All right, 8 minus 6, so that's 2, minus 8, so that's minus 6, and then plus 4, that's minus 2. So minus 2 x hat. What about the y part? So 4 times 5 by 2, so that's going to be 10. 6 times 3 by 2, that's gonna be 9. So 10, 9, 10, 9, and then minus 16. And then minus 12. Interesting. So that gives us 19 minus 28, which should be minus 9 y hat, if I'm not wrong. So this is the position of the center of mass for this weird figure. Okay, and that concludes this video.